So I have proved this exercise. So let's look at this exercise 3. Generalized results from one variable to polynomial ring with several indeterminants. Let's say there are indeterminants. So the first result would be, let's first describe the question. So let's introduce some notation. So let me write. Let's give some notation for indices. So for this, I mean, for example, if you got 1 equals, for example, 1 1 0 0 0 0, then what I mean by n1 would be just x1 x2. Okay, so this is just a summation of return to this form. So it is C and A. Or just call it I, doesn't matter. Just to make sure it corresponds your coefficient with degree. Okay. I think it's better to, let's say it's better to write this. Okay, so now we want to prove fx. Let me simply write fx. There are multiple variable. Okay, fx is a unit. If I don't leave the constant term, which means the term corresponding to 0 0 0 0 equals 0. Is a unit, sorry. And all the others new radical of A. Right, that's what you have to prove. And the idea would be very similar. Actually, so it would be kind of annoying to use this hint for exercise 2 there. This induction is complicated to write it down, but we could just still use method we use in exercise 2 when we prove this question 2 here. We use abstract method. So which is equivalent to prove that what I want to say that describe this as f bar in a quotient prime ideal equals 0 except the constant term, right? Or in other words, that's all what we have to prove. Suppose implies there exists some polynomial with several variables, right? This would imply first is C0 B0 equals 1, and when we want to show that all the coefficients except C0 B0 are in the nil radical, or in this case what we want to show is that minus the constant term how do we work with this? want to show that except this C0, all the coefficients are nilpotent. And it's equivalent to say that in quotient coefficient ring A over X, all the coefficients has image 0. Let's just write it down. So we have Fg equals 1 here, particularly implies this in here, obviously, and this is integral domain. If you have two polynomials whose multiplication is 1, this already implies degree of f equals degree of g bar equals 0. Otherwise, because this integral domain, the degree of f bar g bar would be the degree of g bar plus degree of f bar, and would be bigger than 0. This would be contradiction to the degree of f g bar equals degree of 1, which is 0. Okay, and so this is exactly what we described here. That all the coefficients except the 0 term have 0 image to imply that all coefficients of f except C0 equals 0 in a quotient I x for any I prime of A. In particular, implies all coefficients of f except C0 is in the nilradical of A, and so nilpotent. Conversely, is again very easy, just because nilradical is ideal. If you know nilradical on all the coefficients except the constant, then the summation of that of those monomials is a degree bigger or equal than 1 would be again the nilradical, and so plus a unit is a unit just by exercise 1. Okay, and conversely, we have proved if it is a unit, then the constant term is a unit and all the others are nilpotent. Good. So second statement in the general setting and the several variable case, we have to prove f is nilpotent if and only if all those 0 are nilpotent. In this case, all those C and I are in the nilradical of A. The idea would be, again, this is complicated to write down things by direct computation. So let's still use this abstract argument. So this is equivalent to say that f bar equals 0 for any I prime of A. Okay, so let's just describe this for this much easier. So firstly, nothing to prove for that. If all coefficients nilpotent, they are nilpotent. So what is left to prove is only this. So instead, we'll prove f nilpotent implies f bar equals 0. Nilpotent implies, the idea is that once you quotient by a prime ideal, this is again integral domain. And once you're integral domain, then nilpotent implies 0. And so we are done. You see, this is really a very powerful argument using abstract strategy. No matter it's several variable or one variable, it works equally. Third argument: f is a zero divisor if and only if there exists a non-zero element such that f equals 0. Again, this is by saying that if you got non-zero, there is only one direction we have to prove, which is this one. If you got a non-zero polynomial in several variables which kills f, then it's equivalent. Then it implies there exists zero divisor. There exists a constant coefficient, which means element in A, non-zero, that kills f. And to show this is what we have to do. Can I use induction? Let me think. How about let's use induction on number of variables? Because we already know we already proved the case for one variable, right? So suppose 3 is true. I mean, exists G non-zero kills F implies exists A non-zero kills F for number variable less equal than then I'm going to rewrite if, let's say there are my plus 1 variables. You can always write this just as because this is just this ring as coefficient ring with one variable xn plus 1. By this operation, you could write this as just power of plus 1 0, and then you put some, let's say fi of x. This is in here, okay? And so if there exists some g, of course here, okay? such that Q this polynomial. Obviously, it implies that it kills the coefficients of each xn to the power I of. Let me think. I'm not sure because G also has variable xn plus 1. Let me think. At least, for example, let me write like this. Suppose this addition is from 0 to power n. Then obviously, even if you have wait. So my question put here would be that this implies gx times fix equals 0. This is correct. Then it's okay.